Hello, everybody. My name is DSouza. I'm a PhD candidate at the University of Canterbury, working under the supervision of Dr. Chris Gordon and also collaborating with Dr. John Forbes. Today, I'm going to talk about the disruption of axion minihalos by multiple stellar encounters in the Milky Way. We have one published paper and another paper on arXiv, which has just been accepted for publication. Okay, a little background. QCD axions solve what's known as the strong CP problem, and today they are a candidate for cold dark matter. Now, the universe, so on a cosmological timescale, the universe was initially radiation dominated and then it transitioned to being matter dominated. And during this transition phase that we call as the epoch of matter radiation equality, um, isocurvature axion density perturbations decouple from the Hubble flow, which is the uniform expansion of the universe in space, and they collapse to form gravitationally virilized structures called the Axion Minihalo. Now, these primordial Axion Minihalos that are formed from initial spherical collapse undergo hierarchical merging to give rise to larger Axion Minihalos. And it is these larger Axion Minihalos that we expect to survive until today. Now, we are interested in these mini-halos because they affect the chances for direct dark matter detection experiments here on Earth. Now, numerical simulations show that these axion mini-halos have a spherically symmetric density profile called the NFW profile, which is given by this equation here. And this is a two-parameter equation. So the first parameter is rho sub s, which is called the scale density, and then you have r sub s, it's called the scale radius. Um, for the purposes of our analytical calculations, we ascribe a single parameter to the mini halo, and that we call as the concentration parameter C, which is defined as the ratio of the virial radius to the scale radius r sub s. Okay, and now my research involves calculations of mass loss when a mini halo comes in the gravitational presence of a star. Now, there was this paper by Kavanagh et al. That proposed an analytical model for the mass loss, wherein they integrate the phase space distribution of axions in the mini halo to compute the mass loss in a mini halo during a stellar encounter. Now, we propose two significant improvements to this model. One is called the sequential stripping model, where an outer shells are stripped off before an inner shell is stripped off. Mathematically, what this does is that it affects the gravitational potential of each axion. Now, the second improvement we suggested was post-stellar interaction. The remnant mini-halo is assumed to relax not to another NFW profile mini-halo, but to what's known as a Hernquist density profile mini-halo. And it's given by this expression here. But notice the power of 3 here, whereas the NFW profile had a power of 2. Now, we wanted to ask the question, if a mini-halo undergoes successive stellar encounters with enough time for gravitational relaxation in between encounters, how does the mass loss look like? So we characterize each stellar encounter with a single parameter called the energy injection parameter E sub frac, which is defined as the ratio of the total energy injected into the mini-halo to the binding energy of the mini-halo. And here are our results. On the horizontal axis is the energy injection parameter. On the vertical axis is what's known as the survival fraction, which basically gives you a measure of what fraction of the mini halo survives the stellar interaction intact. Here the blue line is the single encounter case, and I'll focus on the green curves now, which are the multiple encounter case, and the solid line with the circular markers, they are the output of our analytical procedure, and the dashed line with the triangle markers are the output of a numerical simulation done by Shen et al., which I'll abbreviate as S2024. And there's a fair degree of agreement between our their numerical simulation and our analytical calculations. Okay, now going on to a group of mini halos, different mini halos are different masses, so we cannot ascribe a single mass to the entire population. So we calculate what's known as the mass function, which is the number density of mini-halos per unit mass interval. Now, it turns out that initially in the primordial universe, there were isocurvature density perturbations and adiabatic density perturbations. And it turns out that the mini-halos are formed from the collapse of the isocurvature density perturbations. And we use this package called CAMP to compute the mass function of the mini-halos. To do that, we initially calculate the isocurvature growth function using CAMP, and then we use the Shed-Torment formalism to compute the mass function. On the other hand, there are also adiabatic perturbations of axions, and these adiabatic perturbations they occur on significantly larger length scales compared to isocurvature perturbations. And these adiabatic perturbations also can collapse, and they collapse to form what are known as adiabatic halos. And these adiabatic halos are large enough that they can host galaxies. Now, usually the mini-halos properties, so for example, the scale radius, etc., they kind of evolve because of hierarchical merging of mini-halos. But when a mini-halo does fall into an adiabatic halo, these properties freeze. The reason for this freezing is the further merging of mini-halos is prevented inside the adiabatic halo. And the reason for that is there are high virial velocities inside the adiabatic halo. So we again use CAMP, and this time we use the Press-Schechter formalism to compute initially the mass function of the adiabatic halos and then the collapse fraction of the adiabatic halos. The collapse fraction tells you what fraction of the adiabatic axions have collapsed to form halos by any given redshift. So we take the mass function computed from the isocurvature perturbations and we consider the collapse fraction of the adiabatic halos, and this formula gives us the mass function of mini halos inside adiabatic halos. Okay, so now we come to the galactic environment, and we expect the stars in the galaxy to be more or less relegated to the stellar disk in the Milky Way, and we expect the mini halos to be more or less isotropically distributed about the center of the galaxy. And we go about the business of drawing random orbits to simulate the mini-halos in orbit around the galaxy center. So to do this, we assume that the mini-halos are distributed according to the density profile of an singular isothermal sphere inside the galaxy. In reality, we expect the distribution to be more like NFW, but there are subtle issues with the NFW to implement in code. So we use a singular isothermal sphere, which is relatively close enough. And the singular isothermal sphere is a one parameter model. And it has this parameter v sub c, which is called the circular velocity. And the circular velocity is independent of the radius of the orbit. And this sort of simulates sort of emulates the flat rotation curves of the galaxy. Now we use a Monte Carlo procedure to draw random orbits from the singular isothermal sphere. We compute the energy and angular momentum of the orbit, and from these two factors we compute the position vector and the velocity vector of the mini halo today. Now once we've generated the orbit, we want to evolve the orbit. So LB particles is a code developed by my collaborator John. And so LB Particles is a Python implementation of an epicyclic orbit solver, which was initially proposed by Lyndon Bell in his 2015 paper, and this is applicable for bound orbits in a spherically symmetric potential. Now, the state of the mini halo is given by its position vector and velocity vector. Now, given the initial state of the mini halo and a known spherically symmetric potential in the galaxy, LB Particles derives a set of coefficients that can be used to evaluate the mini-halo state at any arbitrary time into the past or into the future. Okay, so when the mini-halos do orbit the galactic center, they pass in and out of the stellar disk, and when they pass through the stellar disk, energy is injected into the mini-halo due to the gravitational presence of the stellar disk. Now, the energy injection parameter for a single disk pass is given by this expression, and this was published in the paper S 2024. Now, our main contribution was to more accurately evaluate the sigma star term, which is the stellar surface density for a single disk pass. Okay, to calculate a sigma star, we first model the stellar volume density in the Milky Way, and that is given by rho star. And we model it in cylindrical coordinates r, z um, for the thin disk and the thick disk of the Milky Way, and that is given by this expression. Now we take the stellar volume density over here, and we integrate it along a single length dimension uh, along the trajectory of the minihalo to give rise to the stellar surface density. Now, in the second equality, I have converted dl to vdt. So now we have an integral with respect to time, and the integrand is rho star v. Now here I have a sample orbit in the graph where time is along the horizontal axis and the integrand rho star v is along the vertical axis. Now the circular red markers are the local maxima, and these are the instants of time when the minihalo crosses the stellar disk. The orange diamond markers are the local minima, and these are the instant of time when the minihalo is furthest away from the stellar disk. One disk pass is considered from one local minimum to the next local minimum with the local maximum in between, and that is the domain of Drage over here. So we get the sigma star or the stellar surface density for one disk pass, and then we stick this into the formula for E sub frac, the energy injection parameter for the single disk pass, and we can evaluate the energy injection parameter for that disk pass. Now, Stucker et al. Proposed a formula for how to add up the energy injection parameters for multiple disk passes. Now, if E sub frac comma I is the energy injection parameter for the ith disk pass, then this formula tells you how to compute the effective energy injection parameter for all the disk passes and treat the overall all the disk passes as a single encounter case. And here the constant P is valid to be determined for our individual problem. Now the S 2024 paper, they did not utilize this formula, but in doing their computation, they effectively assumed P was equal to 2. So P is equal to 2 gives a simple sum over here. And in doing so, they did not take into account the density profile changes that can take place in the minihalo during gravitational relaxation in between disk passes. What we found is that given enough time for relaxation in between disk passes, that the value of P is closer to 1. Now, if I start from P equals 2 and start decrease, if I keep E sub frac comma I constant and I start decreasing the value of P, what happens is the effective energy injection parameter increases. Thus, when we consider a gravitational relaxation, we have an increased effective energy injection parameter, and that results in more mass loss than that was expected in the literature. So now the question is, do we add up the energy injection parameters according to P equals 1 or P equals 2? To decide that, we first have to define what's known as the time. So we first have to define the time scale of relaxation of the minihalo, which we call as the dynamical time, and it's given by this expression. So if the time between consecutive disk passes is less than this dynamical time, we deem that there is not enough time for gravitational relaxation in between those disk passes, and we add up the energy injection parameters linearly with P equals 2, and it's given by this expression. On the other hand, if the time between consecutive disk passes is greater than the dynamical time, then we deem that there is enough time for relaxation in between those disk passes, and the energy injection parameters should be added up non-linearly with P equals 1, and it's given by this expression here. Okay, so we've seen how to compute the mass function of mini-halos within an adiabatic halo by considering the isocurvature and the adiabatic components. That would be the mass function in the absence of stellar disruption. If we take it and stick it in here, that mass function. So dn by dm is the number density of mini-halos per unit mass interval. And if you multiply that by m, the mass of the mini-halo, we get the mass density in mini-halos per unit mass interval. And if we integrate that over all relevant mass intervals, we get the mass in mini-halos in the galaxy. And that would be in the absence of stellar disruption. So that we call it as M sub original. And there is a Monte Carlo procedure we adopt to compute the mass function in the presence of stellar disruption, and it invokes the energy injection parameters we talked about. If you stick that stellar disrupted mass function, which is a suppressed mass function, and we get the mass in many halos in the galaxy in the presence of stellar disruption, and that we call as the M sub survive. Now, if you take the ratio of M sub survive to M sub original, this ratio tells us what fraction, in terms of mass, what fraction of the mini halos that originally fell into the Milky Way galaxy survive until today. Now, S2024 paper, it uses probability density distributions to compute this value, and it gets the value as approximately 60%. And we found that the value is closer to 30% from our analytical calculations, which from our code, which uses the Monte Carlo procedure and a full simulation of the mini-halo orbits. Now, this extra mass that is lost from the mini-halo, it goes into the interminihalo voids called the mini-voids. Now, since the mini-void is significantly larger than the mini-halos themselves, or we expect it to be so, we expect the Earth to be more likely inside a mini-void than inside a mini-halo. And thus the local axion density at the mini-halo increases, thereby increasing the chances for direct dark matter detection experiments. And here is the conclusion slide. For the sake of time, I will leave it up for you to see. But the takeaway message here is the percentage of mini-halo mass that survives until today is significantly smaller than that reported in the literature, thereby increasing the chances for direct dark matter detection experiments here on Earth.